Thank you, Joe. First of all, I'd like to thank organizers for giving me the chance to be here. This is my quantum computer. I will be talking about this quantum computer. Let me introduce myself. This is a picture more than 20 years ago. I'm here. It was at Caltech. I was a member of a quick project. And myself, Hideo Mabuchi, and John Preskill, Daniel Gottesman, and Jeff Kimball, Seth Lloyd, Nicholas Huff, and so on. So many people were there. And Jeff and me, myself, did quantum teleportation experiment there. And since then, I have been working on quantum teleportation for more than 20 years. And I'm a windsurfer. Anyway, these are my collaborators. This is my group at the University of Tokyo, and I have a lot of senior collaborators. We are working on this quantum teleportation chip. By using this one, we can make quantum teleportation inside this chip. The reason why we are working on is that by using this methodology, we can make large-scale quantum computer. In this particular case, it is just one dimension. So teleportation from here to here, and here to here, and then forever. And this methodology can be extended to 2D like this. I mean, this one. So the scale is ultra large. So millions of entangled wave packets. And this is, we can go forever. So it is ultra large scale. So I'll talk about large scale optical quantum computing. As a first step, we created entanglement on a chip like this. So it is actually very tiny. This is 8 millimeters or something like that. We created entanglement on a chip and verified the entanglement on the chip. And by using that technology, we made a teleportation on the chip. This is input state, coherent state, and teleportation, and without entanglement. So that means classical teleportation. And the fidelity is a little bit better than classical limit. So it is on a chip, so it's kind of hard to get higher fidelity. But anyway, we can make a teleportation on a chip. There are two types of encoding for quantum information. One is, of course, qubit. That is superposition of 0 and 1. In some sense, this is digital encoding. And another one is called continuous variable. And it is analog encoding. So this case, information is encoded in complex amplitude of electromagnetic field. That means amplitude and phase. There are two types of qubits. One is called stationary qubit. And another one is called flying qubit. And of course, stationary qubits are spin, ion, atom, or superconducting qubit, and so on. And another one, flying qubit, is of course photons. But there are big difference between them, because in the case of stationary qubit, you don't have to have a real quantum circuit. Quantum circuit is just virtual, and it is a kind of score of which timing you put some control pulse. But in this flying qubit, we need real quantum circuit. So that is very big difference. In any case, we love this qubit because we make quantum error correction. And so we are working on continuous variable, but actually qubit is encoded in this amplitude and phase of electromagnetic field like this. And we call it as hybrid. There is a caveat. We have to know the difference between physical qubit and logical qubit for quantum error correction. As you know, physical qubits are superposition of horizontal polarization of photon and vertical polarization, or up spin and down spin, and ground state and excited state. These are just physical qubits. Only by using physical qubit, you cannot make fault tolerant quantum computation. For fault tolerance, we need some logical qubit for quantum error correction. This is an example, 9-qubit code by Peter Shor. So in this case, one logical qubit needs 9 physical qubits. So we need many physical qubits for fault tolerance. In that situation, photon is the best qubit. It is because we have perfect uniformity and no crosstalk at all. And it can survive in room temperature, and we can use time domain multiplexing. For example, only one beam, but we can use 9 pulses, for example. There are two types of model for quantum computing. 99% of people here knows this one, quantum circuit model. It was invented by Richard Feynman around 1980. And for continuous variable, Seth Lloyd and Sam Brownstein invented this one around 1999. In this case, we set quantum gates and make a circuit, like a conventional computer. There is another model called measurement-based model, or one-way quantum computing. For the case of qubit, it was invented by Rausendorf and Briegel in 2001. And for continuous variable, Nick Menicucci and Peter Van Rook and others invented in 2006. For one-way quantum computing, we need a cluster state like this. And these are called nodes. And actually, in the case of qubit, these are just qubits. But each qubit superposition of 0 and 1, equally superposition of 0 and 1. And in the case of continuous variable, these nodes are superposition of all possible values. And of course, they are entangled each other like this. Naively speaking, this cluster state is a superposition of all possible quantum computing patterns. By using measurement, you can select one of them. So you can change the operation or computation by changing this measurement basis and select one of them. And of course, the measurement result is random. So to eliminate that randomness, we make feed forward. So this measurement and feed forward correspond to quantum teleportation. That is my favorite. So this one-way quantum computation can be regarded as sequential teleportation. And actually, this cluster state is a stabilizer state. So it is extremely error correction friendly. And also, this scheme is extremely powerful for flying qubits because we can make time domain multiplexing. If we use photonic qubits, and if we want to make large-scale quantum computing, we need large-scale setup. So in that sense, there is no scalability. And even worse, the setup cannot be used for different computation. So if you want to make another computation, you have to change the circuit itself. So there is no scalability in this scheme. We can solve all problems, or we can go further by using this one-way quantum computing with time domain multiplexing. For example, we can create ultra-large-scale continuous variable cluster state. We already succeeded in creation of 10,000 wave packet entangled cluster state 5 years ago. And 2 years ago, we succeeded in million. And actually, it is unlimited. We can do it forever. And this is a scheme, very simple. So superposition of all possible state can be a squeeze vacuum and combine this beam splitter and creation of bipartite entanglement. And then one delay, one-way packet delay, and recombine here. We can weave 1D cluster state forever. And we make measurement and feed forward. And changing this measurement basis, this can become universal quantum computation. So it is programmable. Totally different situation from this one. So we can solve all problems. I want to explain in more detail this one-way quantum computing. As I said, this is sequential teleportation. And this is the essence of quantum teleportation. This is arbitrary input, and this is some ancillary input, and make entanglement see phase gate or something, and make measurement. Because of entanglement between this one, we can make some change here by using this measurement. And depending on the measurement result, we make some operation here. And we can retrieve this input state here. This is the essence of teleportation. And this is one-way quantum computing. Again, this is arbitrary input. And in the case of qubit, we use superposition of 0 and 1. And in the case of continuous variable, it is superposition of all possible values here. And again, see phase gate here. And depending on the desired operation U, we change the measurement basis like this. And the output is like this. We can make operation by changing this measurement basis. And we can cascade this methodology like this. We can make U1, U2, U3. And in any case, we prepare this one in advance. And it is called cluster state. And we can create this continuous variable cluster state very easily. The trick is like this. We use parametric process. This is pump photon. And pump photon create signal photon and hydra photon. And in this situation, there is this type of entanglement. If superposition of n, that means if signal photon number is n, then hydra photon number is also n. This type of entanglement. It is called two-mode squeeze vacuum. But anyway, and it is Quadrature non-classical correlation XX, and also P minus P. This is pretty much entangled state. And in the case of wavelengths of signal and hydra are the same, it is called squeeze vacuum. So by using two squeeze vacuum and 50-50 beam splitter, we can create EPR beam or bipartite entanglement. And three of them and two beam splitters, we can create three-mode cluster state. And by using time domain trick, we can do it forever. And first of all, we create bipartite entanglement and then delayed. So the scheme is something like this. One macro node contains two micro nodes. And entangled like this, and this is sort of entangled state. And that's why it is just 1D cluster state. We just make 1D sequential teleportation. And now we want to make this one. So 2D. The trick is that we have to use bipartite entanglement. So bipartite entanglement is set like this and like this and like this like this. And one macro node should contain 4 micro nodes. In that case, you can create this 2D cluster state like this. And there are several proposals to create this state. One original one was by Nikuchi in 2011, and it was called quad-rail lattice. And another one was proposed by Rafa Alexander this year. And he said this is a bilayer square lattice. But unfortunately, these are experimentally difficult to create. But this year, we solved that problem, and we started to create this one. So this gigantic one, by using this scheme. Again, 4 OPOs that correspond to 4 micronodes, and 5 beam splitters, and 2 delay line. And this one is n times longer compared to this one. And by using this trick, I mean, by using 4 OPOs, and only 5 beam splitter and 2 delay lines, we can create this ultra large scale cluster state. The trick is very easy. First, again, we are creating bipartite entanglement like this. So by using 4 POs and 2 beam splitters, we are creating these bipartite entangled wave packets. And then we put 50-50 beam splitter here, combine here. And we create this 4-party entangled state. More precisely, these are wave packets. So if we look at these 4 wave packets, it is entangled like this. And next 4 is again like this. And like this, like this, like this, and so on, like this. And then we put delay line like this. In this case, this delay line is 5 times longer than this one. And this delay corresponds to 1-way packet. So 1-way packet delay. And this guy, 5-way packet delayed. And then combine here. So if we look at these 4-way packets, these are entangled. And overall, like this, it's really messy. But it is exactly like this. So 2D cluster state. More precisely, it is spiral. So it is fold. And in this case, only 5 times. And the size of cluster state determined by this length. And we are doing that experiment. And it is really messy again. We have to check the entanglement. And we can use so-called Van Luck-Furusawa criteria. We invented this one 15 years ago. These are called nullifiers. That correspond to continuous variable version of stabilizer. And these 2 stabilizers these two stabilizers correspond to the entanglement of this one in some index k. And if we satisfy this one in all k, we can prove these entanglement like this. And by using these two, again, these six-party entanglement can be checked. And each index of k, that is time index, we can check this entanglement. So if we satisfy these four inequalities, we can check full entanglement. And for that purpose, we need 4.5 dB of squeezing. And we are creating, we are building this setup like this. So 4 POs, I mean 4 squeezers, and 5 beam splitters, and 2 delay lines, and 4 homodyne measurement. And the reality is like this. 4 POs and 5 beam splitters, but you cannot see. But 2 delay lines, one is fiber delay line in this box, and this delay line is short, so this is just free space. And we did preliminary experiment. Unfortunately, so if all 4 variances less than 4.5 degree, I mean this line, we can say that we created such entangled state, I mean this one. But it is not the case at the moment. But it is very close, and this is very close. This is opposite, so maybe some phase locking is opposite or something like that. Of course, we can solve this one very easily. So I hope we can make a success in a couple of months. There are some big advantage of this scheme. We are now going to more broader band. So original experiment was 10 megahertz, and now we are coming 100 megahertz and going to 1 gigahertz. This is squeezing bandwidth, and it determines the clock frequency of our quantum computer. As you know, clock frequency of conventional computer is several gigahertz. We have to have this clock frequency. Otherwise, who buys such slow quantum computer? Only for Schwarz algorithm. So if we realize this 1 gigahertz, we can handle 1 nanosecond wave packet. And in that case, and the laser coherence time is 1 millisecond, we can make time domain multiplexing up to 10 to 6. This determines this, this number. And operating time is unlimited. It is because we make measurement within laser coherence time. So we already succeeded up to 0.2 seconds. And laser coherence time is only 1 millisecond. So that means we can do it forever. And also, each wave packet can contain more than one photon. That means we can use degree of freedom of photon number. It is extremely important for quantum error correction because we need redundancy of quantum information. More precisely, each wave packet can be a logical qubit. This is an example of logical qubit by one wave packet. It is called GKP qubit, invented by my friends, Gottesman, Alexei Kitaev. He was also in this team, and John Preskill. So by using this GKP qubit and 20 dB of squeezing, precisely speaking, it was 20.5 dB of squeezing, it can be, this scheme can be fault tolerant. But unfortunately, the world record of squeezing is only 15 dB. So this was not good. But we have a very good news now. My colleague shows that even with 10 dB of squeezing, we can make it fault tolerant. So in principle, we can make a large-scale fault-tolerant quantum computer. Of course, in principle. I mean, we have to create this GKP qubit. It is really hard. For that purpose, we are building state synthesizer like this. Superposition of Fock state can make any state because this is basis state. This is our preliminary state synthesizer. First of all, we use two squeeze vacua and making bipartite entanglement like this. So if photon number here is 1, then photon number is 1, 2, 2, 3, 3, 4, 4, and so on. And we have d, small d here, and 3 APDs. And this d is like this, very transparent beam splitter and very weak coherent beam. And when we have a click here, this guy cannot distinguish the photon coming this way or that way. So by using this trick, we can create superposition of 0 and 1 here. And we have 3 of them. That means we can create arbitrary superposition up to 3 photons. And we created, for example, that state. Actually, that is sort of magic state for continuous variable. And we created that state. And a very important point here is that it is without any correction. So we can see the negativity of the Wigner function without any correction. That means we can use it. And also, it is not inside the cavity. It is traveling wave. That's why we can use it. In the case of in a cavity, we cannot use it. If, for example, if you even if you can create a cat state in a cat, you cannot get it out. You cannot use it. And we created, for example, 1 plus 3. That is bigger Schrödinger cat state. We can see 3 negativities of Wigner function. And also three-headed cat state. That is not a good name, though. And up to here, that is just conditional creation. But we have the methodology make it unconditional or deterministic. I mean, we have a quantum memory now. This is our quantum memory. In this particular case, very weak pump beam and create photon pair inside this cavity, red and orange photon. And there is another cavity here. And these two cavities share this mirror or output coupler here. So at the very beginning, this cavity is resonant to this red photon. So this red photon just passed through, but this orange photon is totally reflected here. So stay in this cavity. And this red photon going to APD and herald the existence of this photon. Then when we want to use this photon, we switch this resonance to orange photon, and we can take it out. And we did this experiment. And we stored photons, and we up to here is almost gone of negativity of the Big Bang function, but still 200 nanosecond plus intrinsic delay correspond to 350 nanosecond delay lifetime. And now it was much improved, and the storage time is almost 1 microsecond. So now we are making this one. So by using this trick, so first of all, now pump level is very high. So that means we are making entanglement inside this cavity and outside cavity. And we use this trick. That means we can create superposition up to 3 photons, arbitrary superposition up to 3 photons. And that means we can store these state. And as a first step, we stored superposition of 0 and 1. And we succeeded in the storage. And next step should be photon number resolving detector. These APDs are not inefficient. That is because those are just on-off detector. But by using this photon number resolving detector, we can make it much, much better. And actually, we are fabricating our own photon number resolving detector, because usually photon number resolving detector is really slow. But we invented a neat way to make it broadband. Okay. I'd like to talk about the universality of quantum computing. Again, these are qubits and continuous variable and hybrid. These are universal gate sets for qubits and continuous variables. These are computational basis, 0 and 1 and x. And if we want to change these values, we use bit flip or Pauli X. And in the case of continuous variable, we use X displacement. And conjugate basis, plus and minus, that is superposition of 0 and 1 and plus minus here. And when we want to change the value of plus and minus, we use phase flip or Pauli-Z. And in the case of continuous variable, conjugate basis is P, and we use P displacement. And from computational basis to conjugate basis is Hadamard for qubit, and Fourier transformation for continuous variable. And again, Hadamard transformation is two-dimensional Fourier transformation. It's trivial. And C0 gate is like this, and the continuous variable version of C0 gate is called QND, quantum non-demolition. It's like this. And for universality, we need pi over 8 gate and cubic phase gate. Up to here is called Clifford, and it is called non-Clifford. And fault tolerant creation of this pi over 8 gate is we need a magic state, and it is again we need cubic phase state. So this is continuous variable version of magic state. And up to here, everybody is happy because it is shredding a picture, but we have to use Heisenberg picture. It is stabilizer formalism for qubit, and Heisenberg picture in continuous variable like this. And this is about the universality of our one-way quantum computation. By using homodynamic measurement, we can make universal Gaussian operations. That means we can make all Clifford operations only by using homodynamic measurement, just changing local oscillator phases. But of course, it is not the universal. And for that purpose, we need one nonlinear measurement. I mean, projection onto cubic phase state. And actually, we have the methodology. We invented the methodology. Of course, original proposal was done by, again, Gottesman, Kitaev, and Preskel in 2001, my friends. And but the methodology was really nasty, and not nasty, but too complicated for us, even for us. But we invented this simplified version of this scheme. Only two beam splitters, only two ancillary inputs, but very nasty nonlinear feed forward. I mean, by using electrical feed forward, I mean, that is just classical electrical nonlinear feed forward. We can create optical non-classicality, but it is classical. And putting these non-classical state, we can make it non-classical. Anyway, we can make this setup, and we can make cubic phase gate. And actually, this is projection onto cubic phase state. So it is universal now. And we have the methodology. And we created that magic state and real-time quadrature measurement for web packets. We use a trick of exponentially rising web packet. And also by using such technology, we made dynamic squeezing gate for nonlinear feed forward. 4 years ago, it was analog feed forward. But now we make it digital and very broadband. We solve that problem by using money. Anyway, so we solved this problem, and the final problem was synchronization between optical signal and electrical signal. We put a delay line here. And we used the technology of all-type gravitational wave detectors, multiple type reflection. By using this length, we can make 30-meter optical delay. The reason why we use this delay line, it is almost no losses. If we use a fiber, we have some losses. But if we use this methodology, it is almost no losses. Of course, we need money, again, to have very good mirrors. And now we are building this setup. And experimental results should be coming soon. Let me summarize my talk. We are working on this teleportation chip. That is because by using that methodology, we can make teleportation from here, 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 and make universal quantum computation. And then it can be extended to 2D and large scale. And the final goal should be like this. Only one teleporter here, I mean this one here, and just switch and delay line. And by using this one, we can do the same thing, or even efficient. By using this trick, we can make on-demand creation of cluster state. So everything is classical. And non-classicality only coming here, especially these ancillaries. And the final dream should be all optical quantum computing. And the clock frequency is more than 1 terahertz, even 10 terahertz. In that case, you don't have to use Shor's algorithm, because conventional computed clock frequency is only several gigahertz. If we can use 1 terahertz clock frequency, we can use classical algorithm, and very fast. That is my dream. And for that purpose, we change this one to OPA, optical parametric amplifier, instead of homodynamic measurement. And in this case, everything becomes optical. Thank you for attention.